Hello, welcome to tutorial number 11 of the course Introduction to Linear Algebra at AOU. In this tutorial we will talk about section 3.3 of the book, which tackles such subjects as span, basis and dimensions. Let's start off by a definition of a span. If S is equal to x1, x2 to xk, which is a set of vectors in the vector space Rn, then the set of all vectors in Rn that are a linear combination of the vector S is denoted by span S. In other words, the span of S is equal to the linear combination with these vectors here that are included in S. Therefore, this can be translated as we have seen before, C1 times x1 plus C2 times x2 plus etc. ck times xk, where the C's are scalars that belong to R. Note that span S is a subspace of Rn. Example. This example is related to subspaces, and that we have talked about before in section 3.2, and we have seen, according to the theorem in that section, how we can demonstrate whether a set is a subspace of a vector space. In this example we will learn another method of determining whether a set is a subspace of a vector space. Let's look at this example here. Show that W equal to the set A plus B, A minus 2B, 2A plus 3B, where A and B belong to R. We have to show that this set here is a subspace of the vector space R3. We notice that this set here can be written in terms of two vectors, in terms of A and B. Then we can take these scalars A and B as factors, as such here. So we have A times 1, 1, 2, the vector 1, 1, 2, plus B times the vector 1, minus 2, 3. Therefore, the set W can be rewritten as shown here. A times 1, 1, 2, plus B times 1, minus 2, 3, where A and B are scalars that belong to R. Therefore, W is equal to the span. It means it forms a linear combination with these two vectors, and as a result of this, W is a subspace of R3. Let's look at more examples on this subject here. Let W equal to the set A minus B, 2A, 3A plus 4B, where A and B belong to R. W is a subset of the vector space R3. We have to show that W is a subspace of R3, and we have to find a subset S of R3 that spans W. As we've done before in the previous example, to show that W is a subspace, we will repeat the same process. We notice that this can be written in terms of the vectors A, 2A, 3A, minus B, 0, 4B, and A, the scalars, and B can be taken as factors with respect to the two vectors here. Therefore, W can be rewritten as A times the vector 1, 2, 3 plus B times the vector minus 1, 0, 4, where A and B are scalars that belong to R. Therefore, W forms a linear combination with these two vectors here, two main vectors here, and W is a subspace of R3. To address the second part of the question, find the subset S. It is clear here that the subset S is equal to the span of S, which is mainly comprised of these two vectors 1, 2, 3 and minus 1, 0, 4. Therefore, W is equal to the span of this set here, which is a subspace. Definition of a basis. What is a basis? A set of vectors S in the vector that contains these elements or these vectors x1, x2 to xk in the vector space Rn is said to form a basis for a subspace W of Rn if any one of these two conditions are met. W is equal to the span of S. That means that W forms a linear combination with the element or with the vectors of S. Secondly, S is a linearly independent set. If we can prove any one of these two, that means that the set S forms a basis for the subspace W of Rn. Otherwise, it is not. Note, a set of n vectors S that contains the vectors x1 to xn in the vector space Rn is a basis for Rn if S is linearly independent. And we know how to prove whether a set is linearly independent or not, as we have seen before in section 2.3 of the book. Example: let W be a set that is equal to A minus B, 2A, 3A plus 4B, where A and B belong to R. Let this W be a subset of the vector space R3. Find a basis for W. Okay, we have to find a basis for W. Therefore, in order to do that, we notice that, as we've done before, this set A minus B, 2A, 3A plus 4B can be written into, or can be divided into two vectors in terms of A and B. And we can take the two scalars A and B as factors to obtain A times 1, 2, 3 plus B times minus 1, 0, 4, these two vectors. Therefore, S is equal to 1, 2, 3 minus 1, 0, 4. Therefore, W is equal to the span of S, and S is a linearly independent set. And therefore S is a basis for W. Is a linear independent because it is a span, therefore it is linearly independent, because these two statements are interchangeable. Therefore S is a basis for W. More examples on this subject show that x1, which is equal to the vector x1, is equal to 1, 2, 1, x2, 1, 0, 1, and x3, 3, 1, 0 are basis for R3. We have to show that these three vectors are a basis for R3. Several methods. We can do two methods. Either we can prove that there is a linear combination between these vectors and any vector in R3. Alternatively, we can place these vectors into a matrix and find the determinant. If the determinant is different than 0, therefore the vectors are linearly independent, and therefore the set is a basis for R3. Here in this example, we've chosen the latter method, which is to work with the determinant. So we place these vectors into a matrix, we calculate the determinant, and the determinant is equal to 6, which is different than 0. Therefore, x1, x2, x3 are linearly independent. Being linearly independent, these three vectors are a basis for R3. More examples on basis in R2 and later on the following slide in R3. This is obvious here to us. The vectors E1, 1, 0 and E2, 0, 1 are basis for R2. These are called the coordinate vectors in R2. Since for every vector in R2 can be written in terms of these vectors. Any vector x, a, b can be written in terms of these vectors, coordinate vectors E1 and E2. And E1 and E2 are linearly independent, since each one of them goes into a different direction. They're not in the same line of action, 1. And also, if you calculate the determinant is different than 0. It's the same thing with respect to vectors in R3. And the coordinate vectors in R3 are E1, E2, and E3, as we see here. Any vector in R3, any vector x, a, b, c, can be written in terms of these coordinate vectors. X is equal to a times e plus b times e2 plus c times e3. Therefore, e1, e2, and e3 are linearly independent. We know that they are linearly independent since they are coordinate vectors. Each one of them is going into a different direction. That's one. They're not in the same line of action. Secondly, if we put them into a matrix and calculate the determinant is different than 0. Therefore, they are linear independent, and being linearly independent, it means that they are a basis for the set vector space R3. Let's talk now about dimensions. The definition: the number of vectors in any basis for a vector space V, subspace W, is called its dimension. The zero vector space 0 has dimension 0. In other words, if we have a set that contains a vector with the elements all zeros, we consider its dimension to be 0. For example, R2 has dimension 2, R3 has dimension 3. Why? Because they already have the coordinate vectors as basis for each one of these vector spaces. Example, let S equal to x1, which is a vector that has the components 1, 2, 1. x2 has the component 3, 2, 1. x3 components 11, 10, 7. x4, 7, 6, 4. Find a basis for the subset W equals span S of R3. What is dimension of W? What is the dimension of W? So this question, this question is in two parts. One, we have to find a basis for the subset W, and the second part of the question, we need to find the dimension of this subset. Okay, so in order to address the first part of the question, it has to be linearly independent. In order to find the basis, we know that this set has to be linearly independent. Since we cannot place them into a matrix, because the matrix is 3 by 4 and we cannot calculate the determinant of the 3 by 4, the only method for us to calculate or to determine whether this set is a basis is to put them into this equation here. C1x1 plus C2x2 plus C3x3 plus C4x4 equal to 0. If these C's are different than 0, therefore this is linearly independent. Otherwise, they are dependent. Anyways, so we place these into an augmented matrix. We do the row reduction, apply row reduction technique. The vectors with the pivots of 1 are the basis. Here clearly the first vector and the second vector were transformed into pivots, and the rest are not. So the vectors corresponding to the columns containing leading ones form a basis. In this case, the basis for the subset W are the first two vectors x1 and x2, and since this basis has only two vectors, it is clear that the dimension is equal to 2. This ends our discussion for tutorial number 11, section 3.3. Good luck.